So I know that I said that the last video would be the last for this section, but I wanted to do one more, kind of showing you where these formulae come from, so you're not just sort of coming out of nowhere. So let's start with law of sines. And what I'm going to be relying on heavily in these derivations is I know what sine does in a right triangle. And so what I'm going to try to do is create essentially a right triangle in this non-right triangle. So the way we do that is we're going to drop what's called an altitude from the point there. So I'm basically, this would be the height if we were thinking about the formula for the area of a triangle, half base times height. But I'm just going to go ahead and put that in there. And now what I know is that this here forms a right angle, so I can use sine and cosine, my knowledge from right triangles, to do this. So let's start off with sine of A. That's going to give me h over b. And I'm also going to do sine of b in this case, which is going to be h over a. In each of these formulae, I'm going to rewrite it and solve for h. Now, since h has to equal h, I could actually just set these equal to each other. Whoops. And then divide both sides by a, divide both sides by b. We end up with the law of sines right there. And so we just did a derivation for that. It's a little bit strange. I mean, I kind of drew this triangle suggestively. It's a little bit stranger if you get into this. So if I had said something like, now this was B and then this is A. So it's a little bit strange because a height would actually be over here. So just keep in mind that it doesn't quite work out the exact same way. Technically, we're using the supplement of b over here, and then we would do sine of b as h over, but luckily the supplement works out the same way, and that's why we can extend it to that. Sine of b is the same as sine of 180 minus b. So that's why the law of sines works in that case as well. Okay, so that was law of sines, relatively straightforward, and you could, extend that to get sine of c as well in there. Let's do law of cosines now, and law of cosines actually takes a little bit more work, which makes sense because the formula itself looks more complicated. I am going to rely again on what I know about right triangles to do it, but I'm also going to use the Pythagorean theorem. So let's just say I have my triangle here, A, B, and C. Now, I know that I'm dealing with cosine. So what I'm going to do in this case is I'm still going to drop that, I'll call that h again. Except what I'm more interested in this part is this length and this length. I'll call this length x, and then I could call the other one y, but in order to eliminate multiple variables getting thrown into here, I'm going to call this c minus x. Because whatever x is, the leftover bit has to be c minus x because they have to add up to c. So one thing I could write at this point, which will come into play later, is I do know that cosine of A is going to be x over b. I also know that cosine of b would be c minus x over a. So that's useful information, but I'm not going to use it yet. Before I get into that, I'm actually going to do the Pythagorean theorem. And I'm going to say x squared plus h squared has to equal b squared. And then another formula I could use to try to get h involved again is I could say c minus x squared plus h squared has to equal a squared. So I use the Pythagorean theorem on each of these right triangles here using h as the opposite side in those triangles. Okay, so I have h squared in both, so we're going to use a similar technique that we used above. Solving for h squared, I get b squared minus x squared, and over here I get a squared minus c minus x squared. Okay, so let's go ahead and set those equal to each other. B squared minus x squared equals a squared minus c minus x squared. Now this x is kind of bugging me because in the final formula for the law of cosines, I don't actually have an x in there. So we're going to take that c minus x squared and expand it and hopefully get some cancellation. So it's going to be a squared minus, and then this will be c squared minus 2cx plus x squared. So if you expand that out and multiply and distribute everything, that's what you would end up with. Great. So at this point I have b squared minus x squared equals a squared minus c squared plus 2cx minus x squared. Notice if I add an x squared to both sides, those will go away, so that's good. But I still have an x in my formula. That shows up right there. So here's where I'm going to go back to my original comment, and I'm going to take a look at this right here. Notice I could solve this for x, and that actually would remove any unknowns. I'm back to my lowercase b and capital A. I'm back to my ABC language, and so I can replace that in there, and I'll say that, whoops, let's undo that stroke there. B squared is going to equal a squared minus c squared plus 2 times c times b times cosine of a. Which, at this point, really we're done. This is the law of cosines. I can rearrange things just a little bit. So let's go ahead and add c squared to both sides, b squared plus c squared. Let's go ahead and subtract 2 times c times b times cosine of a. And then that's all going to equal a squared. And so there's the formula. That's one of the alternate versions. We dealt with a instead of c, but we could always go back and redo this using c instead of a. So there you go. These are just more for your personal interest. If you were kind of wondering where those formulas came from, this will show you how to get them. I really like the law of sines because it is pretty straightforward. Law of cosines does take a little bit more effort to figure out. And throughout these derivations, I knew where I wanted to go. I knew what my goal was, and that made it a little bit easier to figure this out. But again, this is totally optional just for your own interest.